Good morning, everyone. It's really a pleasure for me to give a talk today, as I switched just a couple of weeks ago from a poster presentation to the talk. So I'm a postdoc at BI in the non-clinical drug safety department in Germany. And I'm in the investigative toxicology group. So I'm not sure if you're all familiar with investigative toxicology. So I would like to give you a short overview what our goals are and how we can use MPS in investigative toxicology. So in investigative toxicology, we support the whole drug development process. In the early stages of the drug development, we provide risk assessments for targets or chemical classes. And the goal is to have a risk anticipation. And in later stages of the drug development, for example, in non-clinical studies, in clinical trials, or even when a drug is already on the market, we might get safety alerts. And whenever we are getting a safety alert, we try to elucidate the mechanism of toxicity. And here the goal is to have a de-risking and to propose de-risking strategies and also analyze its relevance for humans. So we can use MPS for both ways as a tool for predictive toxicology, but also for retrospective mechanistic investigations. And today I would like to focus on a retrospective mechanistic investigation. As our first MPS case study, we chose agonists for the free fatty acid receptor 1, which is also known as GPR40. GPR40 agonists have been developed for the treatment of type 2 diabetes mellitus. And probably the best known GPR40 agonist is fasagliflozin. It has been developed by Takeda, and it was a very promising candidate in the preclinical studies. It made it to the clinic, and then in the clinical phase 3, it had to be stopped due to drug-induced liver injury. And this was especially interesting for Boehringer Ingelheim, as we had a competitor compound at that time, which we then also stopped due to safety concerns. So until now, many studies have been performed to analyze the mechanism of toxicity, but it's not yet fully elucidated. We are currently investigating the MPS from tissues. And I'm sure that most of you already know the system, as we already had several talks about the system, also quite a lot of poster presentations yesterday. So this is just a very short overview. Here you can see the chips. We have a recirculating system of the medium in the chips. We have on-chip peristaltic micropumps. And tissues offers chips for a combination of organ models. They offer chips for a combination of 2 organ models, 3 organ models, or even 4 different organ models. And one advantage for us is that we are very flexible in the combination of tissue models. We can insert the tissue models in the chips that we have already worked with in static cell culture. Another advantage is that the chips are compatible with live tissue imaging. And also we have permanent access to the different organ compartments to sample media, for example, or to add compounds. For our GPR40 agonist study, we wanted to have a closed in vivo-like situation. So we chose a combination of intestine and liver, and this combination gives us the possibility to mimic an oral substance uptake. We can add the compound to the intestine compartment, which will then be transported through the intestinal cell barrier in the microfluidic channels to the liver compartment. And we can also compare it to an intravenous treatment. And we are currently investigating a 2 weeks repeated dose substance testing. We have an adaptation period of the cells in the chip for 1 day. And after that, we start with the substance treatment. We treat the cells each day with the GPR40 agonists. And also each day we are analyzing the medium. We are analyzing for cytotoxicity with LDH. We are analyzing the cytokine release, liver function with urea secretion and albumin, liver injury with AST, ALT, and GLDH. And as we want to have a really detailed insight in the mechanism of toxicity, in the end, also we analyze the cells with high content imaging, we analyze their ATP content, and we perform a next generation sequencing. So it's really a high content experiment as we have a huge variety of different endpoints. For the cell models, we are currently using ready-made commercially available cell models. For the intestine, we use the epi-intestinal cell model from Mattek. It's a transfer cell model, which you can see here. It's made from primary human small intestinal epithelia cells from a single donor. And already here in the bright field overview, you can see the nice villi-like structure, which you can also see then here in the cryo sections, stained with antibodies and H&E. For the liver, we used the 3D Insight human liver microtissues from Inspiro. They offer human multi-donor primary hepatocytes in a co-culture with Kupffer cells and liver endothelia cells. And we add 45 of these spheroids in the chip. Now, when we started working with spheroids in the chips, first of all, we realized that we have some challenges here to overcome. We wanted to have an easy way to insert the spheroids in the chip, but also being able to remove the spheroids afterwards from the chips. So we started by just simply adding the spheroids in the organ compartment. And what we realized after a period of 14 days in the chips, we got fusion of, we got an aggregation of the spheroids to the PDMS borders in the compartments. So it was impossible for us to remove the spheroids from the chips. And what we also observed was fusion of the spheroids, which then led to necrotic cores. So it was impossible for us to get reproducible data with this setup. So fortunately, Tissues is now also offering chips with ultra-low attachment DIN arrays. And these DIN arrays gives us the possibility to pool the spheroids in the organ compartment, but still the spheroids are separated from each other. As you can see, we have here small little cavities where we add the spheroids, and it's not possible for the spheroids anymore to fusion. And here we could see, we could observe no shrinking of the spheroids. The diameters of the spheroids of day 0 was comparable to their diameter after 13 days. And also we got a stable urea production over 14 days and nicely reproducible data. So today I will show you the long-term repeated oral treatment with the GPR40 agonists. As you probably know, we have to focus on some concentrations in the chips as we still have a quite low throughput. So here we chose to work now with concentrations which are not cytotoxic, as we wanted to get a detailed insight in the mechanism of toxicity. We chose to work with a slightly lower concentration of our BI competitor compared to fasagliflozin, as the BI competitor is also, it's slightly more toxic, but also slightly more potent in vivo. And so with the concentrations we chose, we measured the LDH value each day. And here we couldn't see any significant differences to the control. And what we found was very interesting is that in the intestine, we even got lower LDH values for the treated cells compared to the control. We also made sure that we have a stable barrier function. After 14 days of treatment, we investigated the barrier function of the intestine model, and here we couldn't see any significant changes with the concentrations we used. Also, we couldn't see any distinct differences in the histology of the cells, which you can see here in the cryo section for the control, and here the two different GPR40 agonists. So, of course, we were also interested in the concentration which we actually have then in the liver compartment. So we add 200 micromolar of vasogliflozin to the intestine compartment, which will then get absorbed, transported through the intestinal cell barrier, distributed in the chip, and then eventually gets metabolized in the liver spheroids. And what we found is that we actually have a quite low concentration in the liver compartment. In the beginning, we had only 2 micromolar, and then it increased to around 10 micromolars. So this is actually less than 5% of what we added to the intestine compartment. And there are several reasons for that. So one, of course, might be metabolism. It might be already metabolized in the intestine cells, but then also in the liver spheroids. And another issue or challenge what we have with GPR40 agonists is that they are highly bound to proteins. So it's known for vasogliflozin that it has a human protein binding of 99.8%. And we have some proteins in our cell culture medium. And an issue which we, of course, always have is non-specific binding to PDMS. Now we had a closer look at the spheroids. And in the bright field image, on first view, we couldn't see any differences between the control spheroids and the treated spheroids with the two different GPR40 agonists. We also checked the spheroid area, and here we could see that our treated spheroids were slightly smaller. We also checked the liver function with urea secretion, and here we could also see the urea secretion for the treated spheroids was slightly lower compared to the control condition. ATP content also slightly lower compared to the control. And then we also checked the mitochondrial membrane potential with a mitotracker, and here also we couldn't see any significant differences. Now, in the next step, we performed the high content imaging and analysis of hepatic transporters. We performed 2 different live stainings. One was CLF, which is a substrate for BSEP, and one was CDCF, which is a substrate for MRP2. And for BSEP, we got quite interesting results. In the control spheroids, we can see nicely the bile canaliculi, but in the treated spheroids, there are hardly any bile canaliculi. So we also confirmed this with a high content analysis, and here we could see a significant decrease of bile canaliculi area. We also checked if we have a lipid disorder with an IL-red staining. And here we could see for both of the 2 different GPR40 agonists that we have an accumulation of lipids in the hepatocytes, which you can also see here when we counted the IL-red positive cells, that we have a significant increase of lipids in the hepatocytes after treatment with GPR40 agonists. So as I said before, we also checked the cytokine release in the cell culture medium, and we checked a huge panel of different cytokines. And what we found was that actually most cytokines were below the detection range. We could only measure IL-8 and MCP1. And for both of them, we couldn't see any significant increase of cytokine release after treatment with the GPR40 agonists. We also performed a static cell culture experiment with the spheroids where we induced the cytokine release with LPS. And here, when we tested the different concentrations in the LPS condition and without LPS, we couldn't see any shift of the EC50 value for both different GPR40 agonists. So to sum it all up, we investigated the two GPR40 agonists in concentrations which are not cytotoxic, as we wanted to get a detailed insight in the mechanism of toxicity. We ensured in the intestine cell model that we have a stable barrier function, and we found no distinct differences in the histology. In our high content imaging and analysis, we could see a decreased transport capability of BSAP and accumulation of the lipids in the hepatocytes. So in conclusion, the two GPR40 agonists may lead to cholestasis and steatosis. And as we had no increase in the cytokine release, we have no indication for an inflammation-mediated hepatotoxicity. So we could successfully use our two organ model for a long-term oral exposure of the GPR40 agonists. And what we are currently doing is that we are also performing the next generation sequencing to get an even more detailed insight in the mechanism of toxicity. And with that, I would like to acknowledge all the people who were involved in the project, especially my supervisor, Mario Ballmann, who is also here together with me. And I would like to thank you, of course, for listening. And I'm happy to take any questions you might have.
Thanks, Ilona. Great presentation, and thanks for highlighting investigative talks. Question?
Hi, yes, very nice talk. I'm wondering if you looked at the inhibition of BSAP in a more simpler system.
Like you mean
vesicles.
Just in spheroids without an MPS?
Well, just like BSAP vesicles or some kind of in vitro conventional assay. Did they show inhibition in those simpler systems?
We haven't done that, but it's published. It's already done by several groups, and several groups have checked it and also found that they have a BSAP inhibition also in other systems.
Okay, thanks. Makes sense, right?
Yeah.
Hi, thank you for the great talk. Just wondering if you looked at CYP activity at all in your liver?
We haven't done that yet. We might do that also, but until now we haven't done that.
Mm-hmm. Is that going to be part of your next gen sequencing stuff?
Mm-hmm.
Thank you.
Hey, thanks for the talk. I was wondering, you showed the differences between BSAP and MRP2. Also, like, due to my knowledge, like MRP2 is also lining the bicanalically. I was wondering if you did like a double staining, because it looked like that MRP2 actually the bicanalically looked still intact. So if this is like a very transporter specific like effect you observed?
Yeah, so it might be transporter specific. And we hope that with the next generation sequencing, when we look at the expression of the different transporters, I mean, there are a lot more besides BSAP and MRP2. And with that, we hope that we get a more detailed insight in the differences, if it's specific to some transporters or a general effect to all hepatic transporters.
Thank you.
Thanks.
I have a quick question as well. You hypothesized the mechanism.
Mm-hmm.
Is it known from the clinic what the mechanism of DILI was?
So many people already hypothesized a mechanism, and so the inhibition of transporters is hypothesized by different groups until now, also that there is somehow a lipid disorder. Currently, we are also comparing our in vitro data with in-house in vivo data to see what they found and if that is comparable.
Cool. And one last question, if there's no one waiting. You mentioned about the low exposure to the liver in the tissue system. Is it known clinically what the liver is actually exposed to?
I think it's not known, no. As far as I know, not.
Great, thanks.
Thank you.